you'll get 58. Well, you distribute it and then you cancel things. Okay, so things will cancel out, and this is what you'll be left with. I'm not going to show what cancels. Minus 1.66 AH minus 0.83 H squared, all of this over H. So that's what you'll get. Notice everything here has an H, so I can cancel H. I could factor it out, but I'm just going to cancel, and then one of these goes away, so you'll have just a single H there. So at this point, you have limit H approaches 0 of 58 minus 1.66A minus 0.83H all over 1. So actually, I don't need to write it as a fraction, so because that H cancels. And now what I'll do is I'll let H go to 0. When I do that, this term will vanish because it has an H there. And all you're left with is 58 minus 1.66A. This is the slope of the tangent line, but now that we're talking about a linear motion, that represents the speed, right? This is the velocity of this thing at t equals a. So let's answer part A, okay? Part A, what was the speed of this thing at t equals 1? Well, the speed will be 58 minus 1.66 times 1 is just that. So you get 56.34. And since the speed, just like we normally use like miles per hour, this was meters per second. So the speed of the arrow was 56.34 meters per second. That's part A. Part B says, what's the speed of the arrow at A? Well, we just found that. The speed of the arrow, V, velocity of the arrow at A, is that derivative, or in other words, that slope of the tangent line. That's our powerful formula that we found. Okay, part C says, when will this thing hit the ground? Well, that requires no calculus at all, because if our position was given by this, I forgot the T there. This is the position of the arrow. Then we want to know when the height of this is 0, right? That's when it hits the ground, when the height's 0. And this is an equation. It's actually quadratic, but I can just factor out a t on the right side. Set that equal to 0. I'll just move the 0 to the other side like that. And now that I have two things that multiply to 0, I set them each equal to 0. Of course, this says t equals 0. So I know that the height of the arrow is 0 at the beginning, t equals 0. And then when I take this and I solve that, basically take 58 minus 0.83 t, set it equal to 0. Move things around, divide, blah, 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 you get t equals 69.88. That does not seem right, but it is. Okay, 69.88 seconds. Doesn't seem like that arrow could be in the air that long, but hey, this is a word problem. It's made up. Okay, and then finally, part D is what's the velocity when it hits the ground? So what we need to do to find the velocity when it hits ground is take our velocity, v of a, which we said was 58 minus 1.66a, and we need to replace a with 69.88. When we do that, we get 58 minus 1.66 times 69.88. You should get about negative 58 meters per second. All right, that's it. So I hope that that makes sense. The main idea here, again, going back to all this, is that, again, if you have a position function, the derivative of it is velocity. So we're going to need it. And then you take derivative again, you get acceleration, although that problem we didn't deal with that. Okay, we're going to get into 2.2 now. And this is the derivative as a function. And it's going to be a little bit of a break time for me now. Okay, let me pick up here where we left off. Derivative as a function. So what we've seen so far is that if we're given some function of x, okay, that we can talk about the derivative there, slope of the tangent line, at a specific point, let's say like at 2. Or we could also say, what's the derivative or slope of tangent line at some arbitrary point a? Well, we've used a as our variable to let us know that what we mean is that we're going to let x be some arbitrary number a. But since a is just a letter, we could, if we want, say, what is the slope of the tangent line at, let's say, x? So all we're doing here is using the variable x instead of a. So this right here represents the slope of the tangent line to this function f of x at the point x. So draw a graph. Here's our function f. Pick some arbitrary point. We call it x instead. And then this gives us the slope there. Now, what we can see is that no matter what x we pick, we always have some numerical answer. We have some slope, okay? So what this leads us to is the fact that if we start with the function and you talk about its tangent line or slope of its tangent line at every point, it gives us a new function. So we start with the function of x and we come up with a new function called its derivative. And so the process of taking a function f and turning it into its derivative is called differentiation. So what we can do is we can take the old formula we had where we said limit h goes to 0 of f of a plus h minus f of a all over h. Here we were saying, all right, we're going to let x equal a, and that was our definition for the derivative or slope of tangent line at a. Now what we're going to do instead is we're just going to replace those a's with x's. So we have the derivative of the function f at x is equal to the limit h approaches 0, f of x plus h minus f of x all over h. And this is something you should probably put into your memory bank as the definition of the derivative. This is the derivative of f, is that limit. Now, because this is used so much and it's so important, we have different notations. So here, let me give you some of the notation that we have here. The notation is, let's say, if y is given to us as being some function of x, then the derivative, f prime of x, can also be written as y with the little mark here. We call that y prime. Or we could also call it dy dx. And there's other notations that come later as you go on, take more calculus. There's this one here. This means the derivative with respect to x, meaning x is our variable, of the function f of x. So those are just different notations that we should be aware of. The ones that we'll be using most of the time in this class are those three right there. Okay, now let's take a look at a couple of functions and just the graphs and talk about the slopes of tangent lines and what its derivative or the derivative function would look like. So we'll start out with something basic. Let's say we have a graph that looks like this. Let's say up here it's 1, up here it's -1, and let's say the function does this. It comes this way, straight, flat line there, and it goes this way like this. Okay, and then let's put a dot there, put an open circle here. So this is our function f. Let's talk about what its derivative is. So let's just pick some arbitrary point x, go up to the function, and talk about the tangent line here. Well, the tangent line is flat. It's horizontal. That means it has a slope of 0. So what we know is that the derivative at that particular point would be 0 at that particular point. Now, if we go to another point, pick something, and again, the slope is 0. In fact, any point that we pick over here, the slope will always be 0. So it looks like the derivative of this function is always 0. Now, if we pick some points back here, like pick an x here, go here, and we get a flat line again, flat line here, no matter what we pick to the left over here. So again, it looks like this is going to be true all the time. The only problem that we have here is that something is happening at 0. We have this jump, this break in the graph. So the question would be, what's the derivative of this function at 0? Well, it turns out that in order for your derivative to exist, all right, you cannot have a break in the graph, all right? So here we have a break in the graph, therefore the derivative won't exist. We'll talk more about this later. I just really wanted you to see how these slopes were 0. So it looks like this derivative is going to be 0 whenever x is bigger than 0, and whenever x is less than 0, we know that our derivative is 0. Okay, let's take a look at another graph. Say we have something like this. So we have a graph that goes up and then comes back down. And let's just split it right here. Let's just say that that's the number 2. Okay, here's 1. So looks like if we're anywhere on the left side of 2, any of these points over here, our slope is always the same. In fact, since these go up as you move from left to right, we could say that our derivative here is actually positive, greater than 0, because slope of tangent line is positive, right? That means greater than 0. Here we go look at points to the right, look at our tangent lines there, we notice that they're negative slopes, right? They're pointing down as we move from left to right. So there, our derivative is negative. So again, what would be happening here at 2 is a question. Again, we'll address that later because, you know, what's happening at this weird corner point. So let's get to that later, but for now, let's just recognize that to the left of 2 over here, and to the left of 2, our derivative is positive. To the right of 2, our derivative is negative. So some other things to look at. What if you have function looks like this? Straight line. Well, here, our derivative, take any point. Slope here is constant. It's always the same. Therefore, our derivative is going to be positive because it's pointing up as we move from left to right. But it's always going to be constant. It's always the same number. So I don't know what it is because I don't know the slope of that line, but I can tell you that it's a constant. So what we're trying to get at here is just making sure we understand the connection between a function and its derivative and how they're connected to each other. Let's now talk about you know, when a function would not be differentiable, when the derivative doesn't exist. So we have some graphs that we want to look at. We've seen that before. We haven't seen this. This is called a cusp. And these are different graphs I'm drawing here. Okay, so I want us to look at the points that I have on this graph. All right, don't worry about what's happening, you know, here, 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 because, you know, at those, whenever you're on that part of the graph, the yellow part, our derivative is pretty well defined. We have slopes of tangent lines, right? Anywhere we go in that yellow, we've got slopes of tangent lines. So our derivative exists. It's those points that we have to be concerned about. So look at this one over here. Look at your slope of your tangent line here. That looks like it would be vertical. And remember, vertical lines have undefined slopes. So that becomes a problem. So if we have a corner, if we have a cusp, right? This case right here, our derivative